Hello dear students, so we are back with another class of linear programming problem. So in the earlier class we had discussed about linear dependence and independence of vectors in Euclidean space. So in today's class I will also cover a few more concepts about linear dependence and independence, and I'll try to discuss about spanning set and basis of the Euclidean space. Okay, so first of all let me just discuss about the linear dependence of two vectors. Okay, say linear dependence of two vectors. Dependence of two vectors say u comma v in say e to the power n. Okay, right. So in our last class also we had done it for r vectors. So let me just recall the vectors say x1 x2 up to xr belong to e to the power n are linearly dependent if there exist scalars lambda 1 lambda 2 up to lambda r not all 0. That means at least one is non-zero. Okay, not all 0, such that lambda 1 x1 plus lambda 2 x2 plus up to lambda r xr equal to 0. Okay, so here this 0 is not the ordinary 0 that we talk about. Means it's not the real number 0, it is the 0 of the Euclidean space. So that is actually, this 0 is actually your 0 0 0, right, n tuple. Okay, n tuple 0. Okay, so each of this x1 is not a real number. Okay, lambda 1 is a real number, lambda 2 is a real number, x2 x1 x2 up to xr, these are actually elements in the Euclidean space. Okay, right. So if you have two vectors, say u comma v belongs to e to the power n, are linearly dependent if there exist scalars. So let me just write alpha and beta, okay, because there are only two here, scalars alpha beta, not all 0. Okay, not all 0, that means at least one of them is non-zero, such that alpha u plus beta times of v equal to 0, right? So so out of alpha and beta, out of alpha comma beta, at least one is non-zero. Okay, at least one is non-zero. Okay, so what does that mean actually? At least one is non-zero. So if so we have alpha u plus beta v equal to 0, right? So if alpha is not equal to 0, okay, then 1 by alpha is a real number. Okay, 1 by alpha or alpha inverse. Okay, alpha, or we can write it as alpha inverse, is a real number. Okay, means it is also a scalar. This is also a scalar, right? So what we can do is you multiply this with therefore this alpha inverse multiplied with alpha u plus beta v, this will be alpha inverse of 0. Okay, so if we multiply using distributive property, we can write it this way: alpha inverse of alpha u plus alpha inverse of beta v. Okay, so we are using the properties of vector spaces. So alpha inverse alpha into u plus alpha inverse beta into v, this is equal to 0. So what is alpha inverse alpha? Means alpha inverse alpha is actually 1 by alpha multiplied with alpha. Okay, what is that? This is 1. So it's 1 into u. So it's 1 into u plus alpha inverse beta v equal to 0. So that means u is equal to, I can write it as, it will be minus of alpha inverse beta v. Okay, means this minus is actually the additive inverse, right? Additive inverse of u. because u plus this is 0, so u is the additive inverse of this one, alpha inverse v multiplied with v, alpha inverse beta multiplied with v. Okay, so we can write it as u equal to some scalar, this minus we can take it inside, so it's something like alpha is something like u equal to lambda times of v, where lambda is nothing but minus of alpha inverse beta. Okay, so that means lambda is a scalar. So we say that u is a scalar multiple of of v. Okay, right, so u is a scalar multiple of v. So if alpha is non-zero, then u can be written as a scalar multiple of v. Okay, u is just some scalar multiplied with v. Okay, similarly if beta is non-zero, then using the same calculations we can write it, v will be equal to some mu into u. Okay, where mu is a scalar. Okay, mu is a scalar, that is v is a scalar multiple of u. Okay, so from here we can understand one fact, that if two vectors are linearly dependent, okay, then one of them is a scalar multiple of the other. Okay, one of them is a scalar multiple of the other. Okay, means they are related of the other. So one can be obtained, means one vector can be obtained from the other vector just by multiplying with a scalar. Okay, so this is not always true for any arbitrary vectors. Okay, if they are linearly dependent, then we can find a scalar which is means such that one is a scalar multiple, means one vector is a scalar multiple of the other vector. Okay, now this particular statement also has the converse one. If we have two scalars such that one is a scalar multiple of the other, then can we say that the vectors are linearly dependent? Okay, fortunately that is also true. Okay, note that if u comma v belongs to e to the power n, okay, are scalars, are vectors such that one is a scalar multiple of the other, means one vector is a scalar multiple of the other. Okay, then u and v are linearly dependent. Okay, so we can prove it very simply. So let u equal to lambda times of v. So from here what can I write? I can write it as u plus minus of lambda v. Okay, and this will be equal to 0, that is 1 into u can be written as 1 into u plus minus lambda times of v equal to 0. Okay, so from here can I conclude u and v are linearly dependent? Why? Because 1 is not equal to 0. Okay, two vectors u and v will be linearly dependent if we can find scalars not all 0. Okay, such that lambda 1 into this first one plus lambda 2 into the second one is 0. Okay, so here you see I have got two scalars, one is 1, another one is minus lambda. I do not know anything about minus lambda, whether it is 0 or non-zero, but I am sure that u1 is non-zero. Okay, so immediately I can conclude that u and v are linearly dependent. Okay, so if two vectors are given such that one is a scalar multiple of the other, then immediately we can say that yeah, they are linearly dependent. Okay, right. So if we have something like this, say one vector is u equal to 2, 2, 4, 7. Okay, and this is a vector in e to the power 3, and v is another vector something like 6, 12 and 21. Okay, this is also a vector in e to the power 3. So are they linearly dependent? U and V are linearly dependent or not? Okay, so if you observe carefully, you will see that V is actually, I can write it as 3 times of 2, 3 times of 4, 3 times of 7. Okay, so using scalar multiplication rule, it's 3 into 2, 4, 7, right? Okay, so this is a V is a scalar multiple of U. Okay, V equal to 3 times of U, right? So here these two vectors are, so from here I can conclude this implies U and V are linearly dependent. Okay, because one of them is a scalar multiple of the other. Okay, what we have got is V equal to 3U, so we can write always write it as V 1 into V plus minus 3 into U equal to 0. Okay, so here you see the scalars are non-zero, at least one of them is non-zero. Okay, so immediately we can conclude that U and V are actually linearly dependent. Okay, so sometimes in many of our problems we will denote vectors as column matrix. Okay, so the system is same, say 1 2 3, this is a column matrix. Okay, so this is also an element in e to the power n, just the way of writing is different. Okay, V say I write is something like -1 -2 4. Okay, this is also an column vector in e to the power n, means here 3, this is 3 components. Okay, so how do you add it? U plus V will be just 1 plus -1, then this is 2 plus -2, just the usual way of adding the things, no? So this is actually 0 0 7. Okay, so that's how we add U and V. So can we say that U is a scalar, or U and V are linearly dependent or independent? Okay, so here you see, if we observe carefully, the first two elements of V, they are -1 multiplied with U, right? But the fourth one is third one is different. Okay, so directly we are not getting a scalar multiple. Let us try to verify it using this. Let the definition. So the vectors will be linearly independent if given any scalars, say x and y, x into U plus y into V will be 0 if and only if x is 0 and y is 0. Okay, this is possible. This linear combination will be 0 only when x is 0 as well as y is 0. Okay, for non-zero values of x and y, this is not possible. Okay, so let us check. Let x into U plus y into V equal to 0. So this will imply x into 1 2 3 plus y into -1 -2 4, this is equal to 0. So here this 0 is actually 0 0 0. Okay, so let me do it. So this implies your x, this is twice x, this is 3x, plus this will be minus y, minus twice y, 4y. Okay, this will be equal to 0 0 0. So from there, x minus y, twice x minus twice y, then your 3x plus 4y, this is equal to 0 0 0. Okay, so if you compare, x minus y is 0, the second one will say twice x minus twice y is 0, and the third one will say 3x plus 4y is 0. Okay, so from the first one I get x equal to y, from the second one also I get x equal to y. So if I put it in the third one, it will be, because all these three are simultaneously satisfied. Okay, so once this from here whatever I get, I can always put it in the next. Okay, because these three have to be simultaneously true. Okay, so x equal to y, so here if I put x equal to y, so instead of y I can put x, so this will give us 7x equal to 0, so that is x equal to 0. Okay, and since y is equal to x, so y is also 0. So this type of relation is possible only when both x and y are 0. Okay, so these two vectors here, they are actually linearly independent. Okay, these two vectors are linearly independent. Okay, clear? I hope this is clear. How do we find out whether these things are linearly dependent or independent? Okay, So in many of the problems we will also deal with matrices. Okay, so if I have a matrix, say 1 2 3 4, okay, another this is say 0 minus 1 minus 2 3, okay, and this the third one is say something like 1 1 1 7, okay. So here you see there are 3 rows and 4 columns, okay. Now each row of this matrix can be considered as a vector in what? Each row of this matrix can be considered as a vector in e to the power 4, okay, Euclidean space of 4, dimension 4, okay. This I can consider it as a vector or n tuple in e to the power 4, right? 4-dimensional Euclidean space. This also I can consider this as a vector in e to the power 4, okay. And if you look at the columns, these columns, this is this column 1 0 1, this is a vector in e to the power what? 3, because there are 3 coordinates here, okay. And the second column, this is this one is 2 minus 1 1, this is also a vector in e to the power 3, okay. The third one, this is also a vector in this 3 minus 2 1, this is a vector in e to the power 3, okay. The fourth one 4 3 7, this is 4 3 7, okay, this is a vector in e to the power 3, right? So given any m by n matrix, okay, m by n matrix, each row can be considered as a vector in e to the power n, okay. So let me write it nicely. So given any m by n matrix, each row can be considered as a vector in e to the power n, okay. And each column, what did I say? Yeah, e to the power n, it's okay. Each row can be considered as a vector in e to the power n because there are n coordinates here, okay. And each column can be considered as a vector in e to the power m, okay. So notice the difference, right? So we can talk about linear dependence of columns, okay. So we can talk about the linear dependence or independence of its rows, okay, and columns, right? We can ask whether the columns are linearly independent or not, whether the rows are linearly independent or not, okay. So we can always ask that. So that will be required when we do something called basic feasible solutions or basic solutions of a system of linear equation, okay, right? So what can you say about the columns of this matrix? Say 1 2 yeah, the matrix that I had written earlier. Let me just 1 0 1, this matrix 1 0 1 2 minus 1 1 3 minus 2 1, okay. Let me write it again. 1 0 1 2 minus 1 1, okay, 3 minus 2 1, and this was 4 3 7, okay. So what can you say about the columns of this matrix, whether they are linearly dependent or independent? What can you say about the rows of this matrix, okay? So so in general we can say many things about this. So what is the procedure? Procedure is we convert this matrix into echelon form, okay. Procedure is you convert this matrix to echelon form, and then we can actually find out whether the rows are linearly dependent or independent. Okay, so of course this we will not require this much here, so I'm not discussing this, right? So one thing you can observe here is the third row is actually a sum of the first two rows. Okay, so here the third row R3 is actually R1 plus R2. Okay, so can you say whether R1, R2, R3 they are linearly independent or dependent? R1, R2, R3 linearly dependent or independent, or Li? See, whenever this three vectors or any n vectors satisfy a linear relation of this type, they are always linearly dependent. At least one scalar has to be non-zero. Okay, so here you see here many of the scalars are non-zero. I can write this one as 1 into R3 plus minus 1 into R1 plus minus 1 into R2. Okay, we can always write it this way. So this is a linear combination of this rows R3, R1, R2. Okay, and here at least one of the scalars is non-zero. So here the rows are actually linearly dependent. This implies R1, R2, R3 are linearly dependent. Okay, they are linearly dependent actually. Okay, and similarly you can also find something about the columns, but of course that will require solution of system of equations. Okay, so for the time being I am not doing it because it's a very large matrix. I should have started with a small matrix, say A equal to 1 3, or say 1 3 0 2 5 7. Okay, and say 0 1 0. Okay, so let us check whether the columns are linearly dependent or not. Okay, or linearly independent or not. Okay, so here let x times of the first column, okay, plus y times of the second column plus z times of the third column is equal to 0 0 0. Okay, so what is the procedure? Procedure is x plus twice y plus z, that is 0. This is equal to 0 0 0. Then this will be 3x plus 5y plus z equal to 0, and this will be 7y equal to 0. Yeah. So see, we can just compare this things corresponding coordinates now. So we'll get something like 7y equal to 0. So which will give us y equal to 0. Once we get y equal to 0, we already have from the first one x plus twice y is 0. So from there x is also 0. Okay, and from the third one, the second one, we have 3x plus 5y plus z equal to 0. So we have already got that x and y both are 0. So there is also 0. So this type of relation is possible only when the scalars are 0. That means these columns, the columns are linearly independent. Okay, columns are linearly independent. Okay, right. So this was about linear dependence and independence of vectors, right? Okay, now we have a spanning set, or linear span. Let me just write this: linear span of vectors. Linear span of vectors in e to the power n. Okay, so let x1 x2 up to, or say u1 u2 up to n, let us write it with u1 u2 up to ur belongs to e to the power n. Okay, be vectors. Then the linear span of u1 u2, or say of the set s equal to u1 u2 up to, this is the set of these vectors. Okay, we have started with r vectors in e to the power n. The linear span of the set this s equal to u1 u2 up to ur is this set. The linear span of s, ls, is equal to the set of all linear combinations of the elements in s. Okay, So ls equal to this, say lambda 1 u1 plus lambda 2 u2 plus dot 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 up to lambda r ur, okay, such that this lambda I, they are scalars, okay, right? That is, ls, the linear span of this, is the set of all possible, all linear combinations, okay, all possible linear combinations of the vectors in S, okay. This is called linear span, right? Okay, so ls is the set of all linear combinations of the vectors in S, okay, right? Okay, so for example, so if for example, say a linear span of say you consider S equal to say 1 0 0 1, okay, this one, so which is a subset of e to the power 2, okay, because there are two coordinates here, right? Then the linear span of S, it is the set of lambda 1 into 1 0 plus lambda 2 into 0 1, such that lambda 1 comma lambda 2, they are reals, okay. So it is the collection of all lambda 1 comma lambda 2, such that lambda 1 lambda 2, they are real numbers, okay. So it is the set of all ordered pairs lambda 1 lambda 2, such that lambda 1 lambda 2 are inside the set of real numbers, okay. So you can easily see this is actually equal to the Euclidean space itself, E square itself, okay. We can, at least this is a subset of E square, we already know, and we can also show that any element of E square can be is an element inside ls, okay. Let xy belongs to E square, then xy can be written as in the last class also I told you, I can write it as x into 1 0 plus y into 0 1, okay. So from this line, from this equation, I can easily conclude that this is a member in ls. Why? ls contains only those elements which are of the form some scalar into 1 0 plus some other scalar into 0 1, okay. So this, if we start with any element xy in E square, that element xy can be written as x into 1 0 plus y into 0 1. So it is an element in ls, okay. So any element in E square is also an element in ls. So E square is also a subset of ls. So in this case, ls is already a subset of E square by definition, and here we have also proved that E square is a subset of ls. So we can conclude that this linear span of S is exactly E square, okay. So there are some set of vectors which span the entire Euclidean space, okay. Means all elements of the space E2 can be written as linear combination of the elements in S, okay. And also you see this this set is actually linearly independent. This set of vectors, these vectors are actually linearly independent, we have already done, okay. So any set S which is linearly independent and which also satisfies ls equal to e to the power n, okay, will be called a basis. So then S is called a, S is, my laptop battery is very low, sorry for that, I forgot to put the charger. Of course I'll stop here, in the next class we'll continue. So S is called a basis, okay. So in the next class we'll start what is the definition of a basis of an Euclidean space, okay, right. So in the meantime you just try to revise this whatever we have discussed, right. Thank you.